Oh, you may think anything we need to talk about before we get going? Nothing? Hmm?
Will we have class?
Oh, good question. So if after you get your test 3 grade back, you want to take the final exam, our review day will be November 30th for the final. If you're happy with your grade, then you're done after you take test 3. You don't have to come back. November 30th will be our only class meeting after Thanksgiving, and that's just for people that want to take the final exam.
Our test 3 is next.
It'll be. I'm going to give you the option of taking it on Tuesday or on Thursday. So either the 16th or the 18th. It'll be up to you which one you want to come for. Okay, so let's put that on here. We've got the extra day. Some people might want to take it earlier and get a head start on Thanksgiving break. Some people might want more time to study. I had them with me last time and I forgot. I brought them again.
Okay.
So I've still got makeups out. I'll let you see them. I can't let you keep them, but I'll let you see them before we leave today. And remind me. The last time I just forgot. Anything else? All right. So something a little bit different today. I get to do something other than hypothesis testing. So we are looking at the highlights of section 12.1 and 12.2 today. So our topics here, we're going to talk about correlation, and then we're going to extend that a little bit in the next section and talk about something called linear regression. Sounds a lot scarier than it is. Correlation and linear regression. So the idea in these two sections are we have two quantitative variables, okay, so two numerical variables that we can do calculations with, and we're going to look at how the variables are related to each other. If they are, they may not be related. So when we're doing that, we've got some definitions. Okay. If we have two quantitative variables and we think one may be related to the other or that they're related to each other, okay, that's our idea of correlation. Okay, when we turn it into a word, we get correlation. Okay. So if we think we have two variables that are related to each other, we typically have one variable that we call the explanatory variable, or you can call it the predictor or the independent variable. And the idea there is that variable we expect to have some type of influence, at least some type of relation, okay, that as it changes, our other variable changes. That other variable, the one that responds, okay, is the one we call the response variable or the dependent variable. You do have to be a little careful here. When we're talking about correlation, you have to be careful that you're not thinking necessarily that one variable causes the other variable, or a change in one variable causes the other variable to change. Okay? The best we can do with correlation is just say that it so happens that they both change at the same time. Okay? So they're correlated. That does not mean one causes the other. Okay? All right, so we have an explanatory variable and a response variable, or independent and dependent variable. And usually we set this up the same way in algebra. Okay, so usually our explanatory variable we call x, and our response variable we call y. So the idea is that if we have some equation, and in these two sections we're thinking about a linear equation, so a straight line, then if we change our x value, that means our y value changes. All right, so that's what this is saying. So we make some type of change to our x variable, then we expect a change in our response variable, our y variable. That's all that's going on there. Sometimes it can be kind of tricky to come up with which one you want to call the explanatory, which one you want to call the response. Okay, so sometimes you can look at it both directions, which ours won't be too bad. Okay, where we're trying to figure out which one would be explanatory, which one would be response. Okay. So our goal in this section is just to take two different variables, right? We said they both have to be quantitative for us to talk about correlation. If you have qualitative variables, then there's something you can, something similar you can work with called association. You can say two variables are associated. Here we're talking correlation because we have quantitative variables. Okay, so our goal is just if we have two variables, whatever they are, we want to say, are these two things correlated? And if they are correlated, what kind of relationship do they have with each other? Okay. That's all we're after here. Okay. So definition slides always make it look harder than it is. Okay. So let's look at a data set here. Okay. All right, we got a data set collected from a sample of NFL quarterbacks during the 2018 season. And the data we're going to have the number of interceptions they threw and the number of times the quarterback was sacked. Okay. And we're going to make a scatter plot. So we're going to have interceptions on one axis, sacks on the other axis, and we're going to look to see if these two variables appear to have a relationship with each other. Okay. So let's look at our data first. So there we've got our different quarterbacks in the team that were on that year, and then we've got their interceptions and their sacks. Okay. So what we want to do is we want to see if it looks like there's a relationship between these two things. Does it look like one of these has an influence on the other? Okay. So one way we can do that is we can make a scatter plot. So all we're doing is we're plotting these as points. All right, so if we're gonna call one of these X, one of these Y, right? So like we would have either 16, 24 or 24, 16 would be our point for that one. Depending on how we want to think about it. So here, and again, this is not necessarily straightforward and you could have some debate about it, but which one would we expect to be our explanatory variable? So which one do we think would have an influence on the other? Do we think if a quarterback is sacked more, maybe he throws more interceptions, or do we think if he throws more interceptions, maybe he would be sacked more? Which way around do you think it would be? Which one do you think would have the influence, the sacks or the interceptions? Maybe sacks, okay? Maybe. So it depends on how much you know about football, okay? So maybe if he's got more people in his face trying to tackle him, that would lead to more interceptions, possibly. That's what we're investigating. So here, I think it makes sense, and again, you could debate about it, but here I think it makes sense for us to call sacks our explanatory variable, or X, and then interceptions would be our response variable, or our Y. Okay? And it's okay if we're wrong on this. Okay? We could come back and flip it around. Okay? That's what we're going to do. So we're going to put sacks on the X-axis, interceptions on the Y-axis. Okay? And if we do that, we get a scatter plot. So we're just plotting each one of the data values. Okay, so sacks down here, interceptions on the Y-axis. And what we want to look for is to see if we think we have some type of general pattern. And we're just looking for a general trend in the data. Okay? One thing that's kind of hard to overcome when you're first thinking about this stuff is it's not going to be perfect. Okay? It's not going to be perfect. So we're not expecting like a perfectly straight line or anything. Okay? What we want to see is do we have a general trend. Okay? So there's different ways it could go, right? We could think maybe if they're sacked more, then they throw more interceptions, right? Or maybe if they're sacked less, maybe they could throw more interceptions, right? We're just looking to see if we have a trend there. And on this one, okay, I'll help because it's our first one. On this one, it looks like our goal, we're trying to come up with a line that kind of estimates our data. So ideally, you kind of want a line that goes through the middle of our data points. So it looks like maybe somewhere in here. Okay? That kind of cuts our data in half, right? And you can kind of see then that we kind of are following a general trend. General trend here. So if that's the case, what's our trend? So this is saying, okay, over here we have fewer sacks. Over here we have more sacks. Down here we have fewer interceptions. Up here we have more interceptions. So as our sacks increase, what's happening to the interceptions? They're going down. Okay, so maybe it's a little unexpected. It's a little unexpected. But that's our general trend on the data here. Okay? So this line, I'm taking you back to algebra here. What kind of slope would we say our line has? We've got positive, negative, or zero slope. So that would be negative, yeah. So if our line goes down from left to right, that's a negative slope. So what it's appearing here, and it's appearing to be that we have a trend here, possible correlation. Okay? And our correlation can have two possibilities, right? We can say two things are positively correlated, or we can say two things are negatively correlated. And there we're thinking about this relationship here. If they both go up at the same time, both go down at the same time, that's a positive correlation. If they go opposite directions, like this one, then we have negative correlation. Okay? So this is looking like we possibly have some negative correlation between number of sacks and number of interceptions. Okay? So, okay, that's the idea on our scatter plot. Okay? We want to be more exact than that, okay? But this is our starting place. Okay? This is our starting place. If our data values were just look like they were just completely randomly spread out on the grid, that would make us think maybe we don't have a correlation. Okay? Or let's look at some general situations here. Okay? So if they're all really close to what we would call a straight line, then we would say they have a strong relationship, maybe. And that's what it would look like if they do have a strong correlation. Okay? If it's more like the one we just saw, okay, they're a little more spread out, but they still generally go in the same direction, right? Follow the same line. We would call that maybe a weaker relationship. Okay? Or we could just have just random spread. We would say it doesn't look like there's a linear relationship. Or what about this one? This one we have a pattern, but right now we're only concerned about straight line patterns. Anybody, what kind of pattern would you say we have on this one? Multiple answers here, you can say. What you got? I just didn't hear, I'm sorry. Somebody? Looks kind of like a rainbow to me. Yeah, kind of like a rainbow. Mathematically, right, you would say it's like a possible like a parabola, right, maybe. But it's not a straight line, so we wouldn't be interested in that right now. Okay? You can do correlation and relationships for other relationships, but we're only looking at the linear situation. Okay? So in this case, both of these, what kind of relationship would we have, positive or negative? we have positive. So this would be a strong positive relationship. This would be a weaker positive relationship. Okay. And again, if our slope was going the other way, we would have negative relationship there. Okay. So that's the first thing we look for. We look at a picture and look at our scatter plot to see if it looks like maybe there's some type of linear relationship between the two variables. If we get something like this, something that just looks completely random, we don't have to waste our time going forward. Or if we get something like this, we know maybe we need to investigate some other type of relationship instead of linear. Okay. So let's think about a few variables and think about if maybe they would be correlated or not. Okay. So let's look at a few. And if they are, we want to think about, would it be positive or negative? Here on A, we've got the number of hours you study for an exam and the score you make on that exam. Do you think those two would possibly be correlated? Probably. Probably. So if they are, what type of relationship would you think they would have? Do you think that would be positive correlation or negative correlation? So positive would mean they both go up together or they both go down together. Negative would mean they go opposite directions. Which one do you think on A? Probably positive. So the idea is probably in general, remember we're just looking for general trends here. In general, probably the more hours you study, the better score you're going to make on the exam. There are exceptions, but we're just thinking about in general here. Okay. A negative correlation would mean the more you study, the worse you make on the exam. So this one would be, we would expect probably to have a positive correlation. We'd probably expect a positive sloped scatter plot there. What about on B? We've got the number of miles on the odometer of a used car and its price. So the mileage on a car and how much the car is worth. What do you think on that one? Think they might be related? They probably are in most cases. And then do you think that relationship would be positive or negative? Negative, yeah, because usually as the mileage on a car goes up, its value goes down. Right? So they're going in opposite directions. So that would probably be a negative pattern there. All right, C gives us the pressure on the gas pedal and the speed of the car. Think those two may be related? Probably, right? Probably. So if you put more pressure on the gas pedal, generally what happens to the car? It goes faster. So would that be positive or negative? That'd be a positive relationship, right? As long as your car is working correctly, right, then usually the more pressure you put on the gas pedal, the car speeds up. Right? And then what about D? We got shoe size and IQ for adults. Probably not correlated. Probably not correlated there. If they were correlated, that would mean people with that wear bigger shoes would have a higher IQ, or people that wear bigger shoes have a lower IQ. It have to be one or the other. And those two are probably not related. You do have to be careful with weird things like this sometimes. Okay? Because sometimes you can have weird things that are correlated. Okay? There's let me give you two variables that are strongly positively correlated and see if we can figure out what's going on. Okay? Because you have to remember that just because two things are correlated, it does not mean one thing causes the other. Okay? So here are two variables. These two are, in fact, strongly positively correlated. Okay? And that is how tall a person is and how well they can spell. How well they can spell words. Why do you think that correlation would exist? Taller people can spell better. Why do you? You have any ideas? See, sometimes there's sneaky behind the scenes stuff going on you have to stop and think about. What happens, you have to go back, what happens as a child gets older? What happens to their height? They grow, they get taller, and then what happens as a child gets older with their spelling? Do they normally get better at spelling? Normally. So those two things are both going up, right? They're growing and they're getting better at spelling. So those two things are positively correlated. But it has nothing to do with, okay, it has nothing to do with the one causing the other. And getting taller doesn't cause you to spell better. And they're just correlated. Here's another one. This one's famous. Okay, most statisticians know this one. Okay, two things that don't cause each other, but they are strongly correlated. Okay, so that the amount of ice cream that is sold and the amount of people that are bitten by snakes, those two are positively correlated. Why do you think that could be? Got any thoughts? You got it, yeah. So when ice cream sales are the highest, it's the hot part of the year. When snakes are out and about and people are out around snakes more, that's the hot part of the year. So those two things are correlated. One does not cause the other. You're safe to eat ice cream. Okay? You're safe to eat ice cream. You're in no extra danger of snake bite. Okay? But those two things are correlated. Okay? So you have to be careful assuming causation. Okay? That's what we said. All right, so if we see a pattern in our scatter plot or we think that two variables may be correlated, okay, what we want to be able to do is we want to be able to put a number on it. Okay? We want to be able to say, we said, looking at the pictures, sometimes there's a strong relationship, sometimes there's a weak relationship, sometimes there's not a relationship. So we want to be able to measure that or describe that with a number. So the number we use for that, the one we're going to use, okay, there are a few ways you can do that. But the number we're going to use is called the Pearson correlation coefficient. If you're talking about the correlation coefficient for a whole population, the symbol is the Greek letter rho. It looks like a P. It's the Greek letter rho. Rho. Okay. And if instead we're talking about the correlation coefficient for sample data, which is what we'll always be using, then sample correlation coefficient is a lowercase r. Lowercase r. R. So this Pearson correlation coefficient is always going to be a number between, and it can include, -1 and +1. So +1, that would be a perfect positive correlation. -1 would be a perfect negative correlation. And then numbers that are closer to 0, the closer you get to 0, the weaker the relationship is. Okay? So the closer you are to either +1 or -1, the stronger the relationship, and the sign gives you the slope, the type of relationship that have positive or negative. And then the closer you are to 0, the weaker the relationship is. Okay? And here we're just talking about a linear relationship. Okay? So just if they fall in a straight line pattern. Okay? So here's kind of a picture, right? So if we had an R of 0, then that would mean there's absolutely no relationship between the two. Okay? And then the closer we get to either 1 or to -1, the stronger our relationship is, okay, between the two variables. If you just randomly collect some data, you're never going to see a 1, a -1, or a 0. You're going to be somewhere in between. Okay? Pretty much the only way you ever get a correlation coefficient of 1 is if the math teacher picks out numbers that make it come out perfect. Okay? Same thing's true on the negative end. 0 would even be, I'm not even sure, that would be hard to even come up with where you get exactly 0. I mean, that's our scale. That's our scale. All right. So what we want to be able to do is we want to be able to calculate this correlation coefficient. We're going to use our calculator like we did for standard deviation. Okay, we're just going to put the data in and get correlation coefficient out. Okay? Because here's the formula. I told you we were using our calculator first, so you don't panic. Okay, here's the formula for correlation coefficient. Okay? And there's our correlation coefficient there. A lot of stuff going on in there we don't want to have to mess with. Okay? We got all these summation notations in here and doing a lot of square roots and multiplying and all that. Okay? So these are laborious to do by hand. Okay? We're not going to be interested in doing these by hand. So what we're going to do, we're going to put our data in a calculator and then get the correlation coefficient out. So let's get one, and then when we get to the part where we need the correlation coefficient, I'm going to come around and help you find where that's at in your calculator, okay? In your statistical functions calculator. So let's look at the data set. Okay. So it says calculate the correlation coefficient for the data relating children's ages and their heights. Okay, so first, for correlation, it doesn't matter which one you call X, which one you call Y. Okay, for something we do later, that will matter. But for correlation, the order doesn't matter. Okay? They're either correlated or they're not. But, and just for practice, which variable, so we've got age and we've got height, which variable would we think about being the explanatory variable and which one would we think about being the response variable? Which one do you think would have the influence on the other? Do you think the age would be the influencer or that height would be the influencer? Yeah, so on this one, that's a little weird to wrap your head around, but we're thinking probably age would have an influence on what we get for height, okay, in general. And so we would typically call age our explanatory variable and then height our response. So that's how this table is set up. Okay. So here we've got age in years, and then height is in inches. And we want to come up with correlation coefficient here. Okay, so if you remember on your calculator how you did standard deviation, correlation coefficient is going to be somewhere in there in a similar menu. Okay, so like on mine, I go to stat, and then mine's option number 2. Mine, and a lot of yours will say the mode I'm going to on mine says this. It says a plus bx. That's a linear equation. And we'll see a little later why that's what it's under. So mine, if you got one of these little Casios, that's you hit mode, and then 3 for stat, and then that's option number 2 that we'll go to. And once you hit that, what we're looking for, and we're looking for a table to come up where it asks us for X and Y, and then we can put the data values in. Okay, so let's take a minute. I'm gonna come around and help. Okay, this part takes a minute, but let me come around and help. All right, yeah, yours will just go edit the list, and then you can clear out L1. Yeah, there you go. So you just put the value. Yeah, so you'll just put one column in. Sorry, wrong way. You'll just put the first column in your first column, second column in your second column. On yours, I believe we're going to hit second and then stat, and then we're going to go to 2 variable stats. And we don't have the data in there. You can hit clear. I forget which order. So hit data, and it'll bring up the column. You'll put the first column in your first column, second column in your second column, and I'll come back around. Yours will hit second, and the data button, yeah. And then go over to 2 variable, I think, and hit enter. Cool. And then hit the data button again. And then it'll ask for X1. So that'll be like the first age. And then when you arrow down, it should ask for Y1. That'll be the first height. So you'll go back and forth. get my, and then I'll come back around. Yeah, same thing on here. So you'll hit second, and then the data button, and go over to to variable, and then hit equal, and then hit the data button again, and then it asks for the first X, so that's 1, yeah, and then if you arrow down, it asks for the first Y, and then you do 29.4, and you just keep going down through there like that. Yours is easy, hit stat, yeah, and then go to edit the list. Then you'll put the first column in your first column, second column in your second column, yeah. Yours, let's see. 100%. All right, hit mode, and then you're going to hit 3, and then 1 for linear. And then what do we do? 90. I might have to look yours up. It's been a while since I've been on that one. We'll figure it out though. Yep. And then, yeah, did you already see how to get the data in the list? Yeah, you can hit data. Yeah, so first column and first column, second column and second column. Okay. Yeah, and then you can go back to where you were. Yeah, that's good. I think I skipped up here. I got the thing. Oh yeah, I got it rolling now. Yeah. So you hit the stat button. Oh, we could. Maybe we were on second mode. Hit clear. And now just hit stat. Oh yeah, there we go. And then you can just go to number 1 to edit. Yeah, so you can clear that out, and then you can just do the first column in L1 and then the second column in L2, and I'll come back around. All right, good deal. You're good deal. And then let yours. Okay. So on yours, I think it's the same as his. So you hit mode. Oh no, it's gonna be that mine. And you hit 3 for stat, and then option number 2. That's not mine. And then you'll put the first column in the first column, second column in the second column. And on yours, I think on yours, hit the data button. Very good. So you'll put the first column in the first column, second column in the second column, okay. And then I'll come back around. All right, almost there, almost there. The second trip will only take a minute because it's just telling you what button to hit to get the answer. Okay, I got them in. Yeah, so then yours is, yeah, I think you just hit the stat bar. And then if you scroll over far enough, you should have R. Yep, that should be it there. Oh, no. Yeah, you'll hit stat and go to the list, and then you just put them in the first 2 columns, and then you just go back to calculate. It's on there. It's nice. It's on there. Got it. That one will not do it actually. Yeah. Sweet. Yeah, that's like the only one with stat functions that know that won't do it. So what I'll do, especially for the homework, is I will find an online calculator and post a link, so you can just put the data from. We don't have too many homework problems on these sections, okay? But I'll find an online calculator and post a link, so you can just put the data in there and get the numbers you need out for correlation coefficient and the other stuff. Okay, get yours in. All right, so then you just hit the stat bar button. Yeah. And then just scroll over enough and you'll see R on there eventually. It's pretty far over. Yeah, I keep going. And you'll see A, B, and R. There you go. There's R. Here you will hit second in data man. Yeah. And then number 2 for 2 variable. And then you'll change that second one to L2. Yeah, and then calc. And you should scroll down, it should have R on there. So 0.96 something. Eventually. Yeah. Okay. So once you get yours in, you just hit the stat bar button. And then scroll over as it takes a while. Okay, scroll over and you'll see A, B, and then R is the one we want. There it is. Yep, that's it. Okay. On yours now, Yeah, I think we're gonna hit, shift, let me try it. Shift and no. Maybe we hit AC first, I forget. Yeah, so you hit AC to get out of the list, and then hit shift in that stat menu. And then we're gonna go to number 5. And then we want R, so that's number 3. And then just hit equal. Yep. Here's easier, you just hit the next button over, that stat bar button. And then you just scroll to the right until you see it. It's way over there, you'll see A, B, and R. Number 4. On that, and then down to calculate. You're welcome. Here's. Yep, that's good, that's good. All right, so you do like 1.0 and then hit equal. Oh. Let's see. Goodness, do that out. Oh, okay, I remember. It's been a while. So like you'll go through and put the first column in, and then you have to go back and put the out arrow over, and then you can put the second column in.
Okay.
I forgot that. Here's you hit second in the data button, and then down to 2 variable. Oh no, okay, you can go down to number 4. Sorry, they're different on different calculators. Hit enter, and then you should be able to just go down to calc. And go and then hit enter. Yeah, I think it's like 0.96, and you may have like one typo in the data or something. Yeah, right, almost done. Almost done. You got yours right. Yeah, we already did yours, and then yours died, and yours won't do it right. Okay. Yeah, so we'll get an online calculator posted. Okay. Yeah, so on this one, I think anybody still got their number up? I think R comes out, it's 0.96 something. Okay, so we'll move it around that and call it about 0.964. Okay, so then what's that telling us? So this is really close to +1. So what kind of relationship do we have? Well, it's positive for sure because the sign's positive, and yeah, it's linear. And then since it's close to 1, it's close, strong, yeah. Since it's closer to 1 instead of being close to 0, yeah, we would say it's a strong positive correlation here, okay? Potentially. Okay? What we're expecting. Okay? If we had, just for instance, if we had like 0.352 or something like that, right? Then that's still positive. Maybe we would say we have a weak positive relationship in that case. And if the sign's negative, then same thing, it'd be weak negative or weak positive. I mean, strong negative. That way. Okay. Yep.
When are you posting?
Probably tomorrow.
Okay.
Yeah, probably tomorrow. Yep. Okay. So there's our correlation coefficient. Okay. Let's look at one more together, and then we'll go on to the next section. So the way this would play out, okay, if we were investigating the relationship between 2 variables, okay, so here we're going to look at the number of touchdown passes quarterback has thrown and their salary in millions of dollars, okay, in 2018. So we would make a scatter plot. If we're going to make a scatter plot here, I would think maybe salary would be our explanatory variable, and then maybe touchdown passes would be our response. Like if they're paying a quarterback more money, maybe he's throwing more touchdowns. Or it could be the other way around, really, on this one. If you throw more touchdown passes, then maybe they pay you more money, but usually that would be like in the future, right, when they would do that. So you could think about it either way, really, on this one. So we'd make a scatter plot, and there's our data. That's interesting in itself to look at just for a second. And remember, our salaries in millions of dollars. Wow. You don't have to punch it all in on this one. We'll just skim through. Yeah, this one's a little long. So. All right, so if we make our scatter plot, here's our picture. What do you think about a pattern there? So here we've got touchdown passes going that way, salary going that way. Look like we have a linear relationship on that one. A little iffy, right? Maybe, maybe not all that impressive. If you calculate the correlation coefficient here, okay, let me see what we get. Calculate the correlation coefficient here. R is 0.138. So if we do have a linear pattern, it would be really weak, right? It's close to zero. It'd be really weak positive. Okay? But there is an issue with this data. And again, this kind of comes back to how much of a NFL fan you are. Okay, but if you would have noticed. But so this is 2018 season. 2018, we got Patrick Mahomes making about 4.1 million, but he threw more touchdown passes than anybody else. Okay. So that data point turns out to be an outlier. Okay, it doesn't fit in with the rest of the data. On the scatter plot, that's this point down here. And that's Patrick Mahomes down there. So if we get rid of that data point, and we're just looking at the rest of it, then what do you think? Looks like maybe we've got a little better linear pattern in here, right? Then maybe something like this. So if you get rid of Patrick Mahomes, okay, all of a sudden our correlation coefficient is 0.771 without Patrick Mahomes in there. Okay. So he's messing up our data set. So then that looks like we probably have a positive correlation there, 0.7. That's reasonably strong. Okay, reasonably strong. Okay. That's that one. Okay. All right, so just a couple of things to mention here. Okay, we're not going to spend our time on either one of these last two things. Okay. The main thing there is being able to think about, would two variables possibly be correlated, and if they were, would they have a positive relationship or a negative relationship? And we did some of those, and then calculate correlation coefficient. So either with your calculator, which is what we need to do on test, okay, or with online thing I'll find. Okay. The other two things to mention here, again, we're not dealing with, but okay, is that to be sure you have correlation, you actually do a hypothesis test. You don't have to write this down, because we're not going to use it. We actually have to do a hypothesis test. So we would get a t-test statistic, okay? And this would be how we would calculate our t-test statistic. Now we got our correlation coefficient, and then we got 1 minus correlation coefficient, sample size minus 2. Okay, we're not dealing with all that, okay? But that is technically how you're sure the correlation is statistically significant. Okay? And then one other calculation just to mention, okay, is that if you take our correlation coefficient and you square that number, okay, you get something called the coefficient of determination. Okay. And what that gives you an idea of is what proportion of the variation we see in our response variable is associated with our explanatory variable. Okay. So that kind of gives us an idea of how big of an influence does our explanatory variable have on our response variable. So that's just something to mention, okay? You see that. All right, that's it for 12.1. Okay. Let's look at 12.2 here. Okay. The 12.2, we're just taking it one little step further. Okay. If we have two variables that have a linear relationship, either have a linear correlation with the two variables, then what's the equation of the line that represents their relationship? If they're linear, we should be able to come up with the equation for that line. And coming up with that line that has the best fit to our data, that's what we call linear regression. Linear regression. Okay. So the line we end up with, sometimes you'll see it called the least squares regression line. This idea of least squares is a way that you come up with the line that fits the data the best. Or sometimes you'll just see it called the line of best fit. And when we come up with that, the way we're writing our equation is like this. So here it says we have y hat equals b0 plus b1x. So the reason why sometimes you will see this written as y hat instead of just y is to distinguish it from a data value. So the value we get for y here would be a calculated value, not something you actually found in the data, so we give it a hat. Okay. And then b0 plus b1x, that part should look familiar. Another way you can write this same equation is y equals b plus mx, or normally you're probably used to seeing it the other way around, y equals mx plus b. So b0 is the y-intercept of our line, and b1 is the slope. Okay. And unfortunately, it's not standardized, like everybody uses this form of the equation. Different situations, you get it written different ways. Okay. So here's a long list. Okay, you can write this thing a bunch of different ways. Okay. This is what our textbook uses. Okay, you can just flip it around and write it y hat equals mx plus b, slope y-intercept. Sometimes you'll see it even without a hat. Right? This one's y equals b plus mx. And then most of your calculators are going to say one or both of these forms. It'll say y is ax plus b or y is a plus bx. That makes things a little confusing because on this one, b is the y-intercept. On this one, a is the y-intercept. Okay? So the one with the x is the slope. The one not with the x is the y-intercept. Okay? So unfortunately, there's not like a standard that everybody uses. Okay, so this is our textbook form. Right? So all we need to come up with the equation of a line is we need two numbers. We need the y-intercept, b0 in our case, and we need the slope, b1. Okay. We're going to use our calculator to get these two numbers. Okay. Because here's the formula for the slope. Okay. Yuck. And then here's the formula for the y-intercept. It's not as bad, but yuck. And we don't want to do that. So most of your calculators are going to use one of these two forms. So the numbers we're going to be looking for are A and B. But unfortunately, okay, some calculators do it this way, where A is the slope Some calculators do it this way where b is the slope. So you just need to figure out as we do one, which one your calculator is calling which. But you're probably going to be looking for A and B. Some of you probably saw that you probably scrolled past these two to get to R as we were doing correlation coefficient. Okay? So we'll get there. Okay? And then we're going to round both of those numbers to 3 decimal places. Round both those 3 places. So let's look at a data set. Okay? And then we're going to come up with, we'll figure out if they're correlated. And then if they are, we're going to come up with the equation of the line of best fit. Okay? So we'll come up with that slope and the y-intercept. Okay, so let's look at this one. It says the local school board wants to evaluate the relationship between class size and performance on the state achievement test. Decides to collect data from various schools in the district, and the data from a sample of 8 classes are shown in the following table. Okay. So here we go. We got the class size. We got their average test score. Okay. You want to go to the same place that we just went to for correlation coefficient and put these numbers in just like we did. Okay, if you need help, let me know and I'll come help if you forget a step or something like that. So we're just going to put this in 2 columns like that we were doing. Because our first step, we need to figure out if these 2 variables are even correlated. If they're not correlated, then coming up with a linear model makes no sense. So for R, I'll put the answer up here in the corner. For R, you should get negative 0 point something that rounds to 978. What you should. Yeah, you can do either one. So if you go that way, it's going to call the slope A. If you do the other one, it'll call the slope B. And it gives it to you right there. So just remember the one with the X is the slope, and the other one. Uh-huh.
And then, do I just go
Step bar, yeah. And then just scroll over. It's just way over there, remember. All right, so you might want to go back to the data and double check. Or if you want to, you can hit second in stat and go over and clear the list out. So you maybe had some old data from the last one. Yeah. So you can hit second and then the data button again. And then if you go over one more, it'll say clear data. And that'll clear the list out, yeah. Try typing back. Anything else? Come in there. So this is what you should get for R. That lets you know you got the data tapped in right. Okay. And then probably right there with R, your calculator gives you A and B. Okay. A couple, if they're more like mine, you have to pick them one at a time. And so you have to go back to that stat menu where you picked to see R. And you have to go back and pick to see A, and then go back to pick to see B. So you get both the numbers. But on this one, I give you A and B when we're letting everybody get tapped in. So, well, let me not give it to you as A and B. The slope, if we round to 3 decimal places on this one, come out to negative 1.043. And the y-intercept, we round to 3 decimal places. You should get 103.085. So negative 1.043 for slope, 103.085 for y-intercept. Okay? And you just need to make note of which one's which on your calculator. Okay? If you got one that does it both ways, the graph calculators will do it either way for whatever reason. Do you have any look? Have any look? Get okay, good deal. Yeah, so then you see where A and B were when you were scrolling by to get to R. Okay, good deal. Okay. All right, so what we do with those two numbers, we plug them into our equation for a line, and we get this. Right, so the slope is 103.085. The y-intercept was negative 1.043. If it's positive, this is a plus. And we get our linear equation, and that is the line that fits our data the best. You could spend a whole semester on talking about how you know that's the one that fits the best. It is, okay? You can take my word for it. It's the one that fits our data the best. And if we look at this line drawn on our scatter plot, okay, you can see it fits pretty well. Right? Fits pretty well. Okay. So why do we care? Why do we care what the line is? Okay. So what we've done was we have made a statistical model modeling the relationship between class size and their average achievement test score. Okay. So now what we can do with our model is we can use it to predict values. We can use it to predict values. You do have to be a little careful. You do have to be a little careful. So let's look at when it's appropriate to use a linear model to make a regression model to make a prediction. Okay? Or well, let's say when we should not use it. Okay. So if we don't have a linear pattern when we're looking at our scatter plot, using a linear model makes no sense. Okay. So don't do it. Yep. I was just going. If our correlation coefficient's not statistically significant, we're not testing it. Okay, you can assume if it's close to 1, it's significant in here. But if we do the hypothesis test and it's not statistically significant, don't use a linear model. These last two are where people get in trouble sometimes. Okay. 3 says we should not make a prediction about a value outside the range of our sample data. So we go back to our data here in our sample data. The smallest class size in there was 15. The largest class size was 29. So we should not use this model to make a prediction for a class size of 5 because that's smaller than our smallest data value. Okay. The reason why that doesn't make sense, we can look at our scatter plot. We don't know what happens over here or what happens over here because we don't have any data in those areas. So for all we know, if you get a class size smaller than 15, the students get lonely and they make terrible on their test. Okay? Something like that. Okay? Or if you get a class size too big, maybe everybody gets super motivated and everybody makes 100. Okay? I know that sounds silly, but we don't know. We don't know what's going on out there. Okay? So should not use a regression model to make a prediction outside the range of our sample data. And then the other one, it's a little subtle, is that we should not use a model made from sample data from one population to make a prediction about another population. So here, on this one, who are we dealing with? The local school board or something like that. What did I say? Yeah, the local school board here. All this data comes from the local school area. So we should not use this to make a prediction about a different school system because all of our data came from this one particular school system. Those are situations where we should not make a prediction. Outside of that, we can predict values. Okay, so like there's our data again. Okay, if we want to make a prediction of a class size of 16, what their average test score would be, we can do that. 15 is our smallest database, so 16 is in range. Yeah. So all we have to do, class size is our explanatory variable, our x variable. So all we do is we take 16 and we plug it in for x. So if we do that, plug 16 in for X, work that out, we'll get a predicted average test score of 86.397. Okay, we could do the same thing for 19. Again, you just plug in for X. So 19, plug it in for X. We'll get a predicted average test score 83.268. And you can check, make sure that makes sense with your model. So here we said class size of 19, like an 83. Looks like that's about the right area. Okay. What we should not do, should not do C. C says a class size of 25 at a school in a neighboring district. We should not make that prediction because our data is not from that neighboring district. It doesn't make sense to do that. We should not do D. D says make a prediction about a class size of 45. Our formula will work fine and we'll get a number out, but it has no meaning, okay, because our data values do not go up that big. Okay. That's out. That's out. Okay. Questions there? What's going on? Nothing? Okay, well, that's it. We're not too serious on this. We're just trying to get a taste of it. So we're not trying to become masters of linear regression or anything. You've seen the idea, so. All right, well, we'll stop there. Okay. That's it. That's all the material for this class.